For recording purposes, we're doing the introduction to chemistry today. But first, I'm going to present you with two options. Well, let me be true. Who would you prefer to have as a friend in a fight? Would you prefer King Kong to be beside you or Godzilla? I guess it all boils down to which character you like more. So think on it, and I will launch the polls in a few seconds. All right, so think on it. Yeah. And let me share the results. Well, I'm actually kind of surprised by these results. I thought King Kong was going to win, but apparently Godzilla won. So for those of you all who chose option 2, Godzilla, write down 10 points. The people who chose King Kong, which is option 1, 0 points, right? Keep track of your points. It's what will make class a little bit bearable. All right, let's get started and with the topics. So we're going to start off where we left off, kind of over the summer. I believe over the summer, we did a little bit of the periodic table. I know we did most of organic chemistry, but I know I would have mentioned the periodic table. And of course, anybody here who's doing chemistry would have been introduced to the periodic table. Now, just in case you didn't know, the periodic table is just a list of all the elements found so far on Earth. So things like hydrogen, lithium, there's a whole set here. And you don't need to take this down. For the time being, just listen to me. The periodic table is broken up into rows and columns. Now, I think most of you all know this already. Rows go across, right? Now, rows are called periods. So this is period 1, period 2, period 3, period what? 4. Well, I know some of you all might not use that word. You will say row 1, row 2, row 3, row 4. And I could keep going down, but I don't want to bore you all too much. So, I will have a note on that. For the time being, like I said, just listen, right? Rows are called periods. The columns, the up and downs like this. This is one column, this is two columns. Now, for chemistry, you see this little section here in the middle? I'm going to box it off. This section, you don't actually count it. You don't have to know the reasons why right now. You don't actually count it when we're doing CSEC chemistry. You just ignore that. So this here is the first column. This here is the second column. We skip the whole middle portion, and this will be what? Your third, and just bear with me here, fourth, fifth, sixth, seven, and eight. Now, the columns are called groups. The vertical parts are called groups. Now, for the CSEC syllabus, since we're ignoring the middle portion, there will be 8 groups to be considered. So just to summarize, the periodic table is all the elements found on planet Earth that we have discovered so far. And it's broken up into rows, better known as periods, and columns, better known as groups. And you'll be hearing me repeat this over and over and over to the point where it's going to become so annoying, you're going to remember it for the rest of your life. Also, you will notice that in the periodic table, right? Like, let's choose one element here. Let's choose this guy here. His name is boron. Now, if you're on a cell phone, your screen will be real small, right? It's always better to use a laptop when you're in class, right? You will notice that there's a smaller number and a bigger number. These smaller and bigger numbers obviously represent something when it comes to the atoms. Obviously, it's going to represent something. And of course, I'm going to explain what those numbers represent in great detail. I know a lot of people think they know the basics in chemistry, like the big number and the small number. But when I start to question you or bring CXC type questions on that big number and small number, there's plenty tricks I can pull on you. All right. So, like I said, for those who joined a little late, there's nothing to take down here at the moment. Let's just move on to the next slide. So let's just get started with the basic parts of an atom, right? I'm going to just assume that everyone here knows the three basic parts of an atom: the protons, the neutrons, and the electrons. The protons and neutrons are to the center of the atom. Protons have a positive charge, so everyone keep your eye over here. You'll notice this atom has how much protons? 1, 2, 3, right? Now, protons and electrons are supposed to be equal, and the electrons revolve around the nucleus, which has the protons and neutrons. Protons have a positive charge, electrons have a negative charge, and neutrons, well, their name suggests they have no charge. They are neutral. Now, here's the thing. In a normal atom, I'm not talking about an atom with issues, right? I'm talking about a normal everyday atom. In a normal everyday atom, protons are supposed to be equal to electrons. Now remember, protons have a positive charge and electrons, once again, have a negative charge. So you'll notice that my atom here today, you notice it has 3 positive charges. So look at the red colors. It has 1, 2, 3. So it has 3 protons, and you notice how much electrons it has revolving around it. 1, 2, 3. So protons are supposed to be equal to electrons, supposed to be. Tell me something from school. The amount of neutrons, does the amount of neutrons have to be equal to the amount of protons? Just like how electrons must be equal to protons. Is there any law that says the neutrons must be equal to protons? Like if an atom has 3 protons, does it have to have the same amount of neutrons, which is 3 in this particular case, right? Let me know in the chat. Just type your answers on the chat, right? The answer is no, and you can see it on my diagram here, right? I know I put the neutrons as blue, but I'll put the letter N just to further make it look like neutrons. You notice it have 4 neutrons. You're going to realize in atoms, protons and electrons are supposed to be equal. Neutrons, them don't care. Them is the rebels, right? You can have 5 neutrons, 6 neutrons. Nobody can tell the neutron what to do. All right, he's the bad man, right? So whenever you have an element, right? Remember, let's take this one over here. This here. Let's take lithium, which has a 3 and a 7 in the periodic table. The small number always represents the amount of protons, the smaller number. And the underneath number, let me just get a different color here. The underneath number is the amount of protons plus neutrons. I know some of you are raising an eyebrow because you're looking at where I am on the left-hand side of the screen. And when you look to the right-hand side of the screen, you're seeing something different. Don't worry, guys. For those who are seeing the discrepancy there, I will explain it. I want to prove to you all this is lithium. The top number is 3. How much proton? Now, the top number is the amount of protons. How much protons does it have? 1, 2, 3. And the underneath number is the amount of protons plus neutrons. Notice it have 4 neutrons and 3 protons. 3 plus 4 is what? 7, right? Which means if you take the top number and underneath number, 7 minus 3, you will get 4. Anytime you take the big number and minus the small number, you just always get the amount of neutrons. Always. Okay? Right? Now, here's the thing. The 3, the smaller number, right? His number is actually called the atomic number. The atomic number. Let's put in it here. Atomic number. And the symbol for him is normally Z. Normally. Right? And you see the bigger number, when you add the protons and neutrons, well, his name is the mass number. And the symbol for him normally is the letter A. So in the periodic table, and this used to confuse me in school a lot, in the periodic table, right, the proton number, the smaller number, goes on top. Underneath, the larger number goes underneath. But for some strange reason, I have no idea why. I should probably research it. When you take an element out of the periodic table, when you extract it and you're writing it on paper, you just write it reverse. The bigger number goes on top and the smaller number goes underneath. In other words, the A and Z value gets switched. So that means on the periodic table, right? If it's 3 on top and 7 underneath, if I'm writing it on paper, I have to write it like this for some strange reason. 7, 3. Anybody here, honestly, you can be honest in class, that never hit you? That in school, when you're writing it on paper, the bigger number going on top, the smaller number going underneath. But when you're looking on the periodic table, it's always the opposite. Well, not always, 99% of the case. Right? Just accept it, guys. Just accept it. That is just how life is. Nothing is straightforward in life. Nothing. Right? Nothing. So here's what I need for you all to take down, right? This is all I need for you all to take down for the time being. I'm going to circle exactly what I want you all to take down, right? This thing in green here, right? Take that down. And then take down the note at the bottom of the screen. That's all I needed to take down for the time being. I know some of you are saying, oh God, we have so much other things on the screen. I wonder if this is super important. Not right now. When you finish taking down exactly what I circled, let me know. You can raise your hand and we will move on. Correct. Remember, in the periodic table, the smaller value, the one on top, is always the protons. So protons is 19. And remember, if you want to be real specific, you could put 19 plus, right? Because protons have a positive charge. Normally, protons and electrons are equal. So by default, electrons, when it's negative, is 19 also. And to figure out the amount of neutrons, you minus the big and small number. So 39 minus 13 is obviously 20. And that has no charge. All right, so you don't need to take that down. That was just some practice just to do while we waited on everyone to finish the note. All right, so let's move on to the next slide. Basic stuff here already. Right? And don't worry, guys, if you don't get a chance to take down everything. The class is being fully recorded. Anything you miss, I'll give you the link after class to view it. So let's quickly draw some atoms. Now, if an atom, in CSEC, if they ask you to draw an atom, and an atom has 10 protons, you really think it's a good idea to draw 10 individual circles to represent the what? The protons? No, that's really not a good idea. So I'm going to show you how to draw a general diagram to represent the atom very quickly. For those who came over the summer and was in the physics class also, remember, electrons revolve around the atom. The first shell can hold up to 2 electrons, and the shells after that can hold what? 8. So the first shell is 2, and the rest are what? 8. And remember, protons and neutrons are at the center of the atom. So let's draw sodium. Now, I extracted sodium out of the periodic table. So you notice the larger value on top and the smaller value underneath. Okay? So, quickly for sodium, just quickly on the chart. You can write it in the books too. Calculate the amount of protons, electrons, and neutrons for me very, very quickly. Right? 1 second, guys. Booster. So the smaller number is the amount of protons. So it's 11. That's 11 positive. Protons and electrons are normally equal, right? And neutrons, well, if you minus both of them, 23 minus 11, for some reason, that's 12. I hope I have it correct. Right? So that should be what? Correct there. 11, 11, 12. But now we have to draw it for about 2 marks in the exam. You get 2 crummy marks for drawing it in a CXC exam. A lot of people say, well, I know I do this in Form 2 and Form 3. And you should be happy. You just come back in CXC and you just get marks for it. So let's draw this atom here. So since it has 11 protons, you don't need to draw 11 protons. At the center of the atom, just draw a circle and put 11 or positive 11. That means it has what? 11 protons. It has 12 neutrons. So you can just put the number 12 and the letter N after. So the examiner knows that represents the neutrons. Remember, neutrons have no charge, okay? And now we have to place the 11 electrons orbiting. 11, the first shell can hold 2. So you can put an X. Most people put an X or a dot. So the first shell has 2. Now, that's 2 electrons. Then the next shell could hold 8. 1, 2, 3, 4, 5, 6, 7, 8. Before it's filled. So the first shell filled, in case you didn't know, this is the first shell. The second shell is filled. But 2 plus 8 is what? 10. We need 11. So now we have to put 1 on the third shell. Right? Instead of X's, if you want to put dots, you can also put what? Dots. How much of you all got that correct without my help? Like, you did it in school already a million times, and it's like, it's called easy like squeezy. I guess I don't know if you all know or that expression. Right? Right? And that's 2 crummy marks in a CXC exam, but still 2 what? Marks. Okay? Right? Right? Remember, the first shell can hold 2, and every other shell after that can hold 8. But you fill up the inner shells first, and you gradually add a shell as you go outwards if needed. All right? So take again, I want if you got it wrong, take down the correct answer. Take down the correct answer. So let's say it's June 2026, and you open your CXC exams paper, and you see this question. They want you to draw this carbon, the atomic structure for carbon. I know you can't send the answer, but at least let me know when you finish drawing the diagram. And of course, I will give you 2 crummy marks if you get it correct. So the first thing we need to do is calculate the amount of protons, electrons, and neutrons. The smaller number, which will be underneath if we extract it out of the periodic table. The smaller number is the amount of protons. It have 6 protons. Protons and electrons are normally equal. So that means if it have 6 protons, it's going to have 6 electrons. So and electrons have a negative charge. To get the amount of neutrons, you minus the big and small number. Now, it just so happens, pure coincidence, 12 minus 6 is also 6. So this is a kind of rare instance where the neutrons is equal to the amount of protons and electrons. Remember, neutrons doesn't have to be equal. This is just coincidence. It is equal. So let's go to our diagram. The positive here is the amount of protons. So it has 6 protons. That's this here. How much neutrons does it have? 6. So 6, and you put a little n so the examiner knows we're talking about neutrons. Electrons, some people were a little bit confused. Remember, the first shell can hold 2 electrons, and every other shell afterwards could hold 8. And once a shell is filled, you make a new shell. But this one, we only need 6 electrons. So the first shell can hold 2 electrons, 1, 2. So the first shell is filled. So we have 4 more. We have the next shell could hold up to 8, and we only have 4 to fit. You can put it 4 anyhow. You can put it like this: 1, 2, 3, 4. Some people do it like that, but some people, since it's 4, they like those space it out real nice enough. 1, 2, 3, 4. It's really up to you how you want to put the 4. Just make sure and get the 4 on the other ring. Okay? Right. For those who got it wrong, you think you understand it now? Right? Think you have a better understanding of it now? Right. Right. And if you got it wrong, obviously take down. Right. Let's see what the next slide holds for us. I think these have a little small break there just to cool our heads. Remember, keep track of your points, and guys. So the troll is going to put a situation in front of us again. Let's see which one you choose. You are writing an epic novel. I don't know if anybody here writes novels now, right? But I don't read much, but when I do read a book, I have my preference, right? So you are writing an epic novel. Which one do you choose to write about? Are you a fan of an epic medieval fantasy like Lord of the Rings with dragons and goblins and wizards? Or are you like a sci-fi person, which is option 2? You like space and spaceships and aliens and a whole set of fancy technology, right? So get ready to vote, and let's see which one the class votes on, right? Think on it, think on it. Right, vote, and let's see if you're part of the more popular set or the less popular set. Let me share the results. So it seems that option 1, the fantasy setting, won with 52%, 35 people. But unfortunately, the sci-fi people, you lost by only a mere 3 votes. So the medieval people put 10 points down. The sci-fi people, 0 points, right? Be honest, right? If you chose the sci-fi, 0 points. If you chose the medieval fantasy, this wrongs, you got 10. Keep track of your points. I personally am a fan of option 1. All right, so let's move on. All right, so what are ions? Okay, let me read what it is. And even when most people read a definition in any subject, it doesn't matter if it's chemistry, physics, maths. When people read a definition, it doesn't clear up anything, because definitions have a way of using fancy words, and people just memorize the definitions and they have no idea what it means. I'm hoping my class doesn't end up like that, right? So what are ions? An ion is an atom that carries a positive or negative electric charge as a result of having lost or gained more electrons. All right, let's put that into play here. Let's look at this atom here. You notice that this atom here, I'm going to put N for neutrons, right? You will notice that in this particular atom, there are how much protons? Oops, that's a terrible color there. The amount of protons, look at it here, is the red, 1, 2, 3. There are 3 protons, and how much electrons it have? 1, 2, 3. So the amount of electrons is also 3. I really don't care about the neutrons right now for this explanation. You all remember in maths, positive cancels out negative. Like if you have positive 2 and you're minus 2, you'll get 0. Any overall charge of this atom here, since you have 3 positive and 3 negative, and all the positive will cancel out all the negative. So what's the charge here? 0. Whenever an atom has a charge, an overall charge of 0, like you add up all the protons and electrons, you say it's neutral, right? And that's the fancy word. This here is not an ion. You see, when everything balances out neat, all the positive cancel out with all the negative, that's just a regular boring atom. Nothing cool going on with him. He's regular Joe. However, let's just say, right? Somebody, a thief comes now. A thief comes and he steals one of these electrons. What will happen now, right? You notice it's a different scenario. Now, it still has 3 protons, but it only has how much electrons? 2. So what's the overall charge now? The overall charge here, positive 3. Now, it have more protons than electrons, right? So the positive charge is going to win. And it's going to win by how much? 1. Right? Because positive 3 minus 2 is positive 1. Now the overall charge is not 0. So now this is an ion. An ion is when the charge is not 0. In this particular case, it has a positive charge. So you call it a positive ion. A very, very fitting name because the positive is winning what? The negative. But you know that they like to come up with fancy names for everything. Instead of, some people will call it a positive ion, or they will call it a cation. A cation is another name for a positive ion. That is simply when there's more protons than electrons. Real simple. Okay? Let's move to this example now. P is for protons, N is for what? Neutrons, and the circles around it is what? Sorry, 1, 2, 3, 4, 5, 6. Right, the circles around it are electrons. Tell me something. Is the second atom an ion? Yes or no? Is the second diagram an ion? Yes or no? I drew it a little bit different, but the examiner could draw it like that. Is the second diagram an ion? And the answer is no. That's a regular boring atom. And I can prove it, right? Look at this. It has how much protons? 7 protons. So wait. The protons is 7 positive. And how much electrons does it have? 1, 2, 3, 4, 5, 6, 7. So the amount of electrons is also 7. So positive 7 will cancel out negative 7. But let's change up the scenario now. Let's say that there's an electron over here, and he has no home. He's lonely. He's living on the streets. And he comes up to this atom here, and he says, Can I come live with you guys? And you say, yeah. So the electron smiles and he comes over here now. Right? So look at what happens now. It still have 7 protons, but now it have what? 8 electrons. There's an imbalance now. What's the overall charge here? The overall charge is -1 because it has 7 minus 8 is -1. Since this is also an ion, but more specifically, this is a negative ion. And there's a special name in chemistry for a negative ion. Like if you don't want to call it a negative ion, you call it an anion, right? So the cation is a positive version. That is when there is more protons than electrons. And an anion is when there's more electrons than protons. And that is what this definition is really trying to say. I want you to take down every single thing on that screen. I want the definition. I want my updated diagrams there and all the little explanations underneath the diagrams as well, right? I'm going to give you, I think 4 minutes should be more than sufficient, but 5 minutes, right? So take 5 minutes, take down everything on the screen, please. All right. So let me do something here very quickly. You don't need to write this down. I already explained that the periodic table is broken up into rows and columns. Rows are better known as periods, that's the horizontal, and columns are the vertical, better known as groups. However, there's another way to sectionalize a periodic table. Remember, let me just do this here for you. You all see group 1 here. Remember, this is group 1 here, with the exception of hydrogen, right? We'll get to hydrogen in a little while. Hydrogen is the first element on the periodic table. In real life, when you think about it, and then have metals and non-metals, like I guess general stuff like iron is a metal, aluminum is a metal, copper is a metal. And then it have things that are non-metals, things like oxygen and carbon and hydrogen and helium. And those things are non-metals. And then it have some elements on Earth that haven't kind of quite made up their mind as yet. They ain't too sure if these are metal, and they ain't too sure if these are non-metal. You call those unsure people metalloids, right? And you will see it here on the periodic table, right? Let me just, everything in blue is a non-metal. Everything in pink is a metal. And everything in yellow is a metalloid. However, you could further break it up. Everyone in group 1, with the exception of hydrogen, you call those not just metals, but they have everything in pink is a metal, but everything in group 1 are called alkali metals. So lithium, sodium, potassium, all of those are examples of alkali metals. Everything in group 2 are called alkaline earth metals. Both of them start with A. In school, I have a terrible memory, right? So you can imagine when you have 2 things that start with the letter A and the words resemble, I always get it wrong, right? Group 1 is alkali metals. Group 2 is alkaline earth metals. That's like beryllium, magnesium, calcium. Remember that big section that we skip out? Those are called transition metals. For the time being, you don't have to know what a transition metal is. I will explain that when we move more deep into into chemistry. And then group 7, remember this is group 1, 2, this is 3, 4, 5, 6. Group 7 are called your halogens, and they're going to be a real big part of the syllabus. And the 4 halogens that are on the syllabus are fluorine, chlorine, bromine, and iodine. And group 8, the last group, they are called the noble gases. That's like helium, neon, argon, and I won't call it all to bore you all too much. It's just that the syllabus kind of, how you say, focuses on these areas, group 1, 2, 7, and 8. And they spend a little bit of time on the transition metals, not too much, right? So here's what I want you all to do. If your phone can screenshot it. If you can't, don't let it bug you too much, right? There will be a note on this later on. I know some of you might want to take a screenshot of this, right? But I want to get to hydrogen, right? Hydrogen is a wannabe. Look at this. All the non-metals, look at it, huh? Remember, all the non-metals is blue. Look where all the non-metals is in the periodic table. And all the non-metals, all of them living at least somewhere on the right-hand side of what? The periodic table. Look at it, all of them, except for Mr. Who? Hydrogen. Hydrogen seems, look at where all the metals are. The pink is the metals, huh? A lot of the metals, in fact, all the metals are more to the right, to the left-hand side of the periodic table. Hydrogen, he don't like to hang out with the non-metals. He think, keyword, he think he is a metal. But is hydrogen a metal? No. And you're going to see something as we go along, right? It will become very, very clear as we go along, right? Right? Hydrogen, while he think he is a metal, you see when he around the non-metals, you see when hydrogen liming with carbon and nitrogen and oxygen, when hydrogen liming with them, he just say, he's a metal. I not like oil. I better than oil. I's a metal. But when hydrogen goes to line with the actual metals, when hydrogen goes to line with lithium and sodium, they just laugh at him and they just put him in its place. And you all will see that happening in a little while. Okay? So I hope you all understand the explanation there, right? Someone asked if we're doing the states of matter next week. No, not really. I won't be doing the states of matter as that's too basic. States of matter is just liquids, solids, and gases, right? You can find the notes for that anywhere on Google. You can just type in notes on solids, liquids, and gases, and it'll give you a table, right? For the time being, we have more complex things to do. But don't get me wrong, guys, even though I'm not directly doing solid, liquids, and gases, which is really a Form 1 or a Form 2 topic, I will be mentioning it as we do other topics, and I'll bring it up in the background and explain it while I'm doing another topic, right? Right. So let's move on a little bit here. So what's so important about all the groups? You all ever wondered about that? Why it have a group 1? Why it have a group 2? Why it have a group 3, 4, 5, 6? The guy who made the periodic table was a guy from Russia, right? He saw a pattern. But when it came to all the elements, he saw a pattern. Look at this here. Let's identify something here. If we were to draw all the atoms, let's say that we were to draw sodium. Remember earlier we drew, I showed you all how to draw sodium. You all remember that sodium had how much orbits or how much shells? It had 1, 2, and 3. So it had 3 shells. On the last shell, you all notice how much electrons it had? Didn't it have one electron on its last shell? The last shell, anything on the last shell, you use the word valence to describe it, okay? Sodium has one valence electron. You notice where sodium is on the periodic table? He is in what? Group 1. And that's no coincidence, right? Let me just show you another example. Calcium. If we were to draw calcium, I'm not going to make you draw calcium, but if you were to draw calcium by doing your little calculations, calcium would have 1, 2, 3, 4 shells. And on the last shell, it would have how much electrons? 2 electrons. It would have 2 electrons on the last shell. In other words, I could say there are 2 valence electrons. Look at where the person placed calcium. In group 2. The person who was making or organizing the periodic table realized he put everything based on a pattern. Everybody in group 1, when you draw the atom, will always have one valence electron. Don't get me wrong, all of them going to have different amount of protons, different amount of electrons, different amount of neutrons. But you can bet all your money, lithium, sodium, potassium, all of them, when you finish draw it, will have one electron on the outermost shell, or the last shell, or the valence shell. Look at chlorine. Chlorine, look at it. It has 1, when you draw it, 2, 3, 4, 5, 6, 7. It has 7 electrons on its valence shell. Take a wild guess where chlorine would be placed in the periodic table. He will be placed in group 7. And neon, helium is an exception. You'll get to that just now. Neon has 1, 2, 3, 4, 5, 6, 7, 8. Guess which group he ends up in? Group 8. Right? Now, everybody in group 8 will have 8 electrons, except Mr. Helium. He is just the exception to the rule, and you have to learn to live with it. Helium, when you draw him, he will only have 2 electrons on the valence shell, but you still place him in group 8, right? Now, hydrogen, the reason you put him in group 1 is when you draw hydrogen, he has one electron on the valence shell. But remember, he's a wannabe, right? So they put him in group 1, and it gives the illusion that hydrogen is a metal because he's hanging out with the metals. But hydrogen actually belongs with the non-metals, right? So just to summarize everything I just said here, the groups indicate the amount of valence electrons. The exception is what? Helium, right? Everybody with me so far, right? You don't need to take down everything here, right? This is too much to draw. The only thing you're going to take down is this. What is so important about groups 1 to 8? And then you're taking down this. All right? I know I didn't do carbon, but carbon has 1, 2, 3, 4 electrons. So you can take a wild guess. Carbon was placed in group 4. Right? Right? You know the usual. When you take it down, when you finish taking it down, just raise your hands. Right? Silence. So that's the answer one question, right? Let's take group 1. Let's just take group 1 as an example. We know that everyone in group 1 is going to have one valence electron. But will they have the same amount of shells? We're only focusing on group 1. For example, sodium, we could see it here, has how much shells? It has 1, 2, and 3 shells. And on the last shell, it only has 1 electron. So potassium, right underneath the K, right underneath sodium, is also in group 1. Will he also have 3 shells and 1 electron? The answer is no. Potassium will have a different amount of shells. Now, I know the answer. It will actually have 4 shells, right? And on the last shell, you can bet all your money. On the last shell, which is the 4th shell, it will have 1 electron. So, and as you go down, the amount of shells increase for group 1. That happens for all the groups. But the idea is that even though each of them have different amount of shells, the amount of electrons on that last shell will always be 1. And the same thing for group 2. Everyone in group 2 is going to have different amount of shells, but I guarantee you on the last shell, it will have 2 electrons. I'll bet all of your money on it, right? So let's move on. And that's going to be answered in the next slide there. Go downwards. Group 1, group 2, group 3, 4, 5, 6, 7, and 8. Now we're going to talk about the periods. The periods go horizontal. This is what? Period 1. Period 2. Let's help out here, right? Period 3. And, well, you won't need to cross period 4 for the exam, okay? You notice these 3 guys here? Let me know in the chat. Sodium, chlorine, and argon. Which period all of them are which period do they belong to? Which period do they belong to? Sodium, chlorine, and argon. All 3 of them belong to one period. What is that one period? It's not a trick question. People is always saying I'm trying to trick them, right? I'm not trying to trick you. Straightforward question. It's period 3, and you all are correct. You notice all of them, they have different, look at it, all of them in period 3, and all of them have different amount of valence electrons. Remember, sodium is in group 1, so he have 1 valence electron. Chlorine is in group 7, so he has 1, 2, 3, 4, 5, 6, 7. And argon is in group 8, so he has 1, 2, 3, 4, 5, 6, 7, 8. So obviously the amount of valence electrons different. But you notice something? Because all of them, you place them in group 3, you notice all of them have 3 shells. Look at it. They have different amount of valence electrons, but all of them have the same amount of shells. So everything in the same period, like everything in period 1, will have 1 shell. You can bet all your money. Anything in period 2, when you draw them out, will only have 2 shells. And I think you all get the drift here. So take down this now. What is so important about periods? Everyone in the same period has the same amount of electron shells. The amount of electrons and valence electrons is going to differ, but the amount of shells itself is the same for each period, right? Let me know when you're finished, as usual. And by the way, you see a first question in CXC. Sorry, your second question, question 2 in the CXC exam. You're going to get 6 questions. The second question, you see everything we just do from the beginning of class, this common question 2. And you get about 12 to 15 marks for that question. Geez, get a host of the easy questions like this now, which is real good news for the CXC exam. Move on to the next small break here, a little break minutes, right? So the end of time has come. It's time for you to meet your maker. Which option do you prefer here? They prefer to be thrown to the sharks by a group of pirates as they go arg and mock you, or you go on a polar expedition and you're ripped apart by a swarm of polar bears there. Think it through, think it through, think it through. These are choices we all have to make. Let's get the polls running here. Let's see the winner. And the winner is the Sharks. Now, personally, I would have chosen the polar bears. Not me and sharks, and not me and the ocean. All right, so for the people who chose death by the pirates and the sharks, 10 points. We polar bearians, 0 points. Update the amount of points you have. Right, at the end of class, we'll see who has the most. All right, let's get ready to move on. So what are isotopes? Well, this is where the neutron comes in, right? Remember we said we know a lot about protons and electrons. We know most of the times protons and electrons are equal. Quick question. What determines the name of an atom? The protons, the electrons, or the neutrons? Well, let's say that you find, I'm sorry, that will give away the answer. So back to my original question. What determines how you name an atom? The protons, the electrons, or the neutrons? Who determines the main name for an atom? What do you all think? And I know a lot of people are going to say neutrons because my tone suggests that the answer was neutron, right? But that's just to mislead you. The answer is protons, guys. Protons, okay? For example, let's take boron here, right? I know you can't see it too well, but boron, I'll write it back big here. Boron is what? He has, well, when you extract it out of the table, right? I think he's going to be, I can't really see it. Let me just call it. You're seeing a 5 on top and I think it's a 10. It doesn't really matter. I think it's 11. I can't really see. Anybody can see there? I can't see. Let's take oxygen, fluorine. Oh God, my eyesight's so bad. I don't have my glasses. All right. Somebody say it's 10. That's just a bad example, right? Let me take the potassium because we did potassium, right? So we did potassium. So when we extract potassium, right? Remember, the big number was 39 and the small number was 19. The small number is the amount of protons, right? When you are naming an atom, like let me say you find an atom, the amount of protons determines the name. Remember, potassium, normal potassium will have 19 protons. It has 19 electrons. And how much neutrons again? When you minus it, you get 20. That's potassium. We did this calculation earlier, okay? The name of an atom is determined by the amount of protons. So that means, right, if one day you went and find a very strange atom and it had 19, let me just say, sorry, I'm going to put X here. We don't know the name of the atom as yet, so we're going to call it X. So you discover this new atom, and it had 19 19 protons, but instead of 20 neutrons, so it had 19 protons, so it's going to have 19 electrons. But let's say the amount of neutrons was 22. Anybody wants to tell me what the top number would be? The top number would not be 39, huh? Because remember, the top number is protons plus neutrons. So how much is, it has a different amount of neutrons now. 19 plus 22 is how much? 41. Do you know that the name of this atom will still be potassium? The name of an atom is determined by the amount of protons. It doesn't matter if it have a different amount of electrons. Let me just say it's an ion. It doesn't matter if it have a different amount of electrons, and it doesn't matter if it has a different amount of neutrons. You still have to refer to it as Mr. Potassium because he has 19 what? Protons. However, I know there is a difference, right? Because at the end of the day, even though both of them is potassium, one of them has 20 neutrons and the other one has 22 neutrons. Technically, that's the only difference between two of them, right? They have the same amount of protons, same amount of electrons. It's just the neutrons is different. So, to be more formal now, his official name will be potassium 20, and his official name will be potassium 22. So you can tell the difference between the two. It comes like you have two twins. Two twins might look the same, but you give them different names so you can tell them apart. These two are isotopes of each other. Isotopes have the same amount of protons, so you call them by the same name. But because they have a different amount of neutrons, right? You have to give it a slightly different name. It's an isotope of each other. And elements have different what? Isotopes of each other. So the one that we're going to take into account here for my explanation is oxygen, right? So let's go back to the oxygen here. There are many different versions of oxygen, you know. Look at this. The one on the periodic table, I know you can't really see it too good, right? The one on the periodic table that you see is this one here. It has an oxygen with 8, when you extract it out of the table, it has a 16 here and an 8 here. But there's another oxygen, one with 17 here and 8 here. And there's a third version of oxygen with an 8 here and an 18 here. You notice all of these oxygens have the same amount of protons, but the top number is different. Why is the top number different? Because the amount of neutrons is different. So his top number is 8 plus 8, which is 16. His top number is 8 plus 9, which is 17. And his top number is 8 plus 10, which is 18. So his official name is oxygen 16. His official name is oxygen 17. His official name is oxygen 18. Okay? But when you look in your periodic table, you just only see one of them. You just only see oxygen 16 in your periodic table. Anybody can tell me why? If there are 3 different types of oxygens, 3 different isotopes of oxygen, because each of them have different neutrons. Why you just only see one in a CSEC timetable? Why did we put all 3, boy? Why don't they put all 3? Right, and some people are getting it correct. They know the answer to this one. Because that's the most popular one on Earth. The CSEC timetables, well, I should only say CSEC. Most timetables, periodic tables, only put the most popular one on Earth. there is more oxygen 16 on Earth than oxygen 17 and oxygen 18. Don't get me wrong, you could actually go buy a more expensive periodic table. And you could, it's like a post-it now, where you can lift off this now. And behind that, you will see 17. And if you lift off that piece of paper, right behind it, you'll see 18. You will see all the different isotopes of each element. But the cheap periodic tables, this only show you the most popular one on Earth. And only mention, you just only hear about the other ones when you're reading your textbook. You don't actually see it in your periodic table. Right, so I hope you all understand what an isotope is. An isotope is the same element. They have the same amount of protons, but because they have different amount of neutrons, they are considered to be slightly different from each other. Right? Right, take down this. And remember, the protons is what determines the name of an atom. And of course, the name of an atom determines where it is placed in the periodic table, which means the amount of protons really determines where it's placed in the periodic table, because the protons determine the name, right? Take down everything as circled there. Okay. So a lot of people mix up isotopes and allotropes. Isotopes is the thing we just did. That's the thing with the same protons and different amount of what? Neutrons. An allotrope has to do with how you combine atoms. Okay? If sometimes you take one type of atom, the most popular one on the CXC timetable is carbon, right? I think everyone here has seen carbon at some point in time. You know your pencils? The tip of your pencil is what? Carbon, right? Carbon is an atom, right? Now, in case the carbon we're talking about here is the most popular type of carbon, right? It's carbon 12, right? Which is really, it has a 12 here and a 6 here, right? Carbon is in group 4. Now, carbon is not expensive. You could go in the ground, like carbon real cheap, right? But it all depends on how you connect carbons. If you take carbon, like all of these dots here represent carbon, right? All of these dots here represents a carbon atom. If you link them up, and I'll explain how to link them up later on, right? But if you take a whole set of carbon atoms and you link them in this particular pattern, you just get what? Diamond. Carbon is cheap. But if you link it up in a particular pattern, you just get something completely different. The feel of it is completely different. You just get diamond. And as we all know, diamond really expensive, right? But if you take that same carbon and connect them in hexagons, in layers of hexagons like this, you just get what? Graphite. Graphite is the tip of your pencil, right? And these two things are completely different. Both of them made of carbon. But because you link them or join them up different, you just get two completely different materials. Not even different materials, completely different materials. One expensive, one worth a fortune, and the other one is worth nothing. You call these allotropes of each other. Each of these is an allotrope. Allotropes are different forms of an element, right? In the same physical state. When I say the same physical state, both of them are solids. Okay? And this is the most common one on the CXC exam. And they will ask you to draw this diagram. And then they will ask you to draw this diagram. Right? So how much of you are going to have problems drawing these two diagrams? Raise your hands and I'll go help you draw it. I'll go help you draw it step by step. Right? Right. So let me start. First of all, right? Do me a favor. I'm going to show you how to draw it, right? Take down this. And then we will draw each diagram one by one. But do me a favor. Get different colors. Get a red ink, a blue ink. I guess I'll lead pencil. That's great, right? And I'll show you how to draw each one by one. Right? We'll start off with the diamond. But at least how to draw it to get full marks in the exam, right? Because that's what you really care about, right? Getting full marks in the exam. So here's what you're going to do. To draw a diamond, just put one red dot. That's not red. Draw a line going downwards and put one more red dot. Just do that for me. Simple. I will tell you when to switch your pens. Right? That's all I want you to do. From this dot, 3 legs going to come out. 1, 2, 3. At the end of each leg, put a dot. 1, 2, 3. 1 second, guys. Phone wasn't on silent. Right? Grab another color pen now. Probably blue. I'm gonna grab blue. Right. From one of them on this end, draw a line going down and put a dot. And then from on this end here, draw a line and put a dot. Right? Now, remember, from each dot, 3 legs supposed to come out, right? 1, 2, 3. Do that for me. And then from this one, 3 legs supposed to come out, right? 1, 2, but you see the third one? Make it touch this one. 1, 2, and make this touch this one. And at the end of each one, just put a dot. And where these two meet, put a, and that is it. You don't have to go into much detail. You'll get full marks for that in the exam. I'm telling you, you'll get full marks. You don't have to worry too much then. Right? The examiner will get the idea that you know what you're doing. Right? So, and you just walk away smiling and everything will be okay. All right? Everything will be okay there. Right? So I hope that helps a little bit there. So now we'll draw the what's the other one? The graphite, right? The graphite gives a little bit of trouble to draw. Not the graphite is just hexagons joined together. Right? Right, I'm going to erase this here, right? Right. You don't have to draw plenty hexagons, believe me. I'm going to use red here. Just draw one. Right, one. I'll draw it in different colors. One. Just draw 2 like that. 2 hexagons. Right? You realize one hexagon side fills in the other side of the other one. And all you have to do at each vertice, just put a dot. That is all you have to do. Right? Right. And when you do that, draw the same exact thing directly below. Directly below, do the same exact thing. Draw a kind of hexagon here. 1, 2, 3. You're doing a replica of it. Right? When you finish it, just grab a different color. You can probably grab a blue ink or a pencil or something, right? And all you're going to do is draw dots between corresponding points. Like you see how these 2 points line up, right? You just draw a dash line. These two, dash line. These two. And that is it. The examiner will get the idea that you know what you're doing there, right? Just draw a few dash lines. You don't have to draw all. You just draw a few, connect a few of the corresponding points from the top part to the underneath part, and you get your full marks. And you walk out the exam room smiling. Right. So this is where we're going to start off next week. I know we only have 5 minutes. Next week, we're actually going to do something called happy and sad atoms, right? It's supposed to be a fun way of explaining how atoms achieve happiness in the chemical world. All right. So we're not going to do this today, but I know you all probably want to do one more. And I'm sure it's at the end of class. Anybody here hungry? Anybody here hungry? Like you're just waiting for class to over to run in that kitchen and get a snack? Anybody here? Well, if you want one of these to appear in front of you right now, keep in mind, it will look exactly like how it looks in the picture. Look at the both of them. Which one would you prefer to appear in front of you right now? All right. Which one? Take a good look. I unfortunately am not getting any of these because I have none of these things in my kitchen right now. I'll be lucky if I get bread and cheese right now. All right, let's take the vote. Let's take the vote. I have a good feeling this one's going to be close. All right, let's have a look at the results. And the clear winner here is option 1, the chicken. So chicken people, 10 points. Fries people, 0 points. So guys, give me a total of how much points you have for today, right? Oh, by the way, on the chat, I'm sending the link for today's recording. It will be uploaded in 24 hours. Save that link, right? If you're unable to get the link, like you can't save it on Zoom, not a problem. You just WhatsApp me at 1-868-712-2652. State your full name and tell me exactly what you want. Don't say send anything. Remember, I just how you say? I just teach real subjects, right? So when you say send the link, you need to say what class, even if it's maths, you have to tell me which maths class, right? So when you message me, state your full name so I know who he is, and tell me exactly what you want. Be real specific so I can help you. All right, so it seems that some people have 40 points. Congratulations to the people, right? Right, some people did not have, some people got 10 points. Oh, Lord. Anyway, guys, it was good. So I hope you all enjoyed. Oh, by the way, let me show you what the homework looks like. Look at it. When you go to that link, you will see look at it. Homework balancing equations, part 1, part 2. And I'll upload today's video over here. It's really easy to follow, don't worry. It's really, really easy to follow. Right? So guys, with that in mind, see you all hopefully Sunday for physics. Take care, guys. Have a good one, and thanks for coming to class and participating. Congratulations again for people who got 40 points. Well done, well done. Most people got tutor from what I'm seeing here. Bye all.